Hello everyone, welcome back. Let us continue our discussion on reinforced concrete design. We are in the 8th week and this is our third lecture. In this lecture, our topic is flat slab, right? Now, before we go into the details of the design of flat slab, let us first quickly go through the frame structure that very often we encounter in our residential and commercial buildings. So if you look at the frame, so we have a combinations of beams and columns, right? So as you can see here, this is a frame and here you can see there are some columns. Okay, so these are columns and there are beams here. So in this direction, we have slabs, which are supported by beams at the four edges. So, for example, if you take this slab, it is supported by four beams at the edges. Now, these four beams, they transfer the load from the slab ultimately to the column, right? So in this combination, as you can see, we have this corner column, and if you add one more slab here, what you will get is this is your intermediate column. Now, when we construct this type of structure, we need to develop the formwork that gives provision for this beam and this slab. Now, you have already gone through the detailing of a beam and detailing of slab, and you have seen if you have a slab here, if I just draw the cross section here, we have a slab which is coming like this, and then we have a beam. Now, just imagine the construction. So we have, this is the stirrup, that is the shear reinforcement. Then we have here the main bars. And if you recall, for slab, we have also reinforcement coming, right? So it is like this. And then we have slab reinforcement in other directions. Now, depending upon the location, we can have this top reinforcement or not. If it is at the corner, you have seen that we have some additional reinforcement. Now, at least these reinforcement, this at the bottom will be there. And you can imagine when you construct this type of structure, first you have to make a formwork here, and then another formwork for the slab, and then you place the reinforcement and then pour the concrete here, right? And then whatever the necessary steps for construction, like compact the concrete and then cure it properly, and then you will get the beam slab combination. Now this is sometimes very difficult to construct. The question that comes in our mind, can we not support this slab directly on this column? Then what happens? Obviously, we don't need this beam anymore. Then directly place the slab over this column, and then you can imagine instead of this formwork, we can actually have flat surface for the slab, and that will be much easier to construct. The question is, can we design that? It has other advantage from the architectural point of view, because when you have a frame structure, you can always see these beams. So for structures where aesthetics has some importance, then we may avoid these beams and directly place the slab over the columns. So to answer the first question, can we place the slab? Answer is yes, of course we can. But for that, we have to have some additional design requirements. The reason is, when you come to this support, for example, if you come here, what happens? We have negative reinforcement, and not only that, if we remove this beam here, then what happens? We have a slab which is like this, and suddenly there is a column coming out, and because of that, what happens? As you all know, these sections are critical. We have to be extremely careful about these sections, and we will see how we can design, because there will be high hogging moment here, and also the shear force is very active in this region, and therefore when we have a sharp change in cross sections, instead of providing a beam which was earlier there, now we have a direct connection between the slab and the column. We need to take care of all these design requirements. So to answer the first question, whether we can design this, yes, of course. Next, how to design it. So for that, let us first quickly go through the definitions of flat slabs and what are the structural components when we design a flat slab. Let us quickly go through it. So as per definition, it is a slab that rests directly on the column without beam. Okay, that we have already explained, without beam. Now, obviously, the moment we have a slab directly resting, as you can see here, then significant bending moment and shear force will act at the junction of this column and slab. We have to take care of that. Now, as you can see here, one of the common practice is to widen this column head. As you can see here, it is widened. So if the column is like this, widen it, and then there is a drop panel. So we have a drop panel here, and then on top of drop panel, we have this slab sitting. So when we design, we have to actually design the size of these drops, and we have to design the reinforcement accordingly. Now, sometimes we may avoid, if the situation is permitting us, then we can avoid this drop panel, but as the moment and shear force increases, it is always better to have a drop panel here. So we can have a drop panel, or sometimes we can avoid it depending upon the situation. Now, when we design this, couple of things we have to keep in mind. The drop panel, obviously, at this portion, it is much thicker compared to the slab thickness, which is here. Now, when we have, say, two supports, as you can see here in plan, then this slab, flat slab, behaves like a plate, and there will be two regions critical. So one region is called the column strip. So when we talk about the reinforcement, so there is a region around the column. This is the column strip. Obviously, for the other column, we have a similar strip. Then this part at the middle between two column strip is what we call the middle strip. Now for column strip, it is the design strip that having a width of 0.25 L2 but not greater than 0.25 L1 on each side of column center line, where L1 is the span in the direction of in which the moments are being determined. Okay, and L2 obviously perpendicular to L1. Okay, we'll see in a minute how to decide that, but the fact is column strip will be 0.25 L2 not greater than 0.25 L1. Then there will be middle strip. So from the geometry, we can first find out the width of the column strip, and from that width, we can also design the size of the middle strip, right? Of course, the question is how to find out the bending moments and shear force in this region, that we will see in a minute. The first thing we have to keep in mind, when we'll provide the reinforcement in a flat slab supported on columns, there will be column strips and there will be middle strips, and their schematic diagram as you can see on your screen. Now, before we design flat slab, let us first see what are the advantages. Okay. So the first advantage is it provides, as I told you, a smooth level ceiling, because if you have a beam in a frame structure, you can always see the beam hanging. So in this case of a flat slab, we do not have a beam, so we have a smooth and flat ceiling, which is aesthetically more pleasing. Now, obviously, when we design a frame without beam, it allows actually to reduce the overall story height. And since the beams are not there, obviously, it is easier and simpler to construct. Because I already showed you, for construction, you first have to provide a formwork for the beam, and then you have to place the reinforcement properly. There should be proper connection between them, and then you have to pour the concrete. Now, for the same system, when we actually remove one component, which is beam, the overall structure is relatively lighter. That means we transfer less load to the foundation, and of course that is advantageous because your foundation size will be less, the load transfer to the soil will be less. So compared to a structure where you have slab, beam, column combination, flat slab is a better option. Now, from the cost point of view, because you have less material used, cost is also relatively cheaper compared to a beam column structure. Now, when we talk about the behavior, now let us slowly move over to the design part. First, we have to analyze the structure, and as you can see on the screen, you have this column strip, middle strip, and depending upon whether it is an edge column or intermediate column, the size of the column strip is also going to vary. Now, the structural behavior of a flat slab, which is actually a flat plate, is similar to a 2A slab, right? So that means when we will provide reinforcement, recall the 2A slab design, we had reinforcement in design in two directions. Here also we will see in a minute how we can actually evaluate the bending moments in two different directions and accordingly find out the steel requirements. Now, the slab portion along the column lines in both perpendicular directions can be treated as beam. This is important. So if you have a column strip, as you can see here, this is the column strip. So this column strip, we can actually treat it as a beam and then design it as a beam. Now, the moment we consider them as a beam, as you can see, we have supports here, supports there, and then support here. So whenever we have support, then obviously at the support we'll have hogging moment, and in the mid span we have sagging moment, right? So that we have to keep in mind, and you'll see as we design this flat slab, we'll consider hogging and sagging moment. Now, we consider, so first point to be noted here, we consider this as a beam and then accordingly design, but we have to consider two orthogonal directions. Now, let us first see the deflected profile of a flat slab. As you can see here, we have deflected profile here. So we have points marked A, B, C and D are the support points where we have, you see the dotted line, that is the column supporting the slab. And then obviously you can see the deflection curve, and at the supports we have zero displacement where we'll have hogging moment. See the orientation of the curvature. At the middle part we have deflection, and the maximum deflection is here at the point I. Recall we have in two orthogonal directions, we have column strip and middle strip, right? So we'll design it accordingly. So for the middle strip, obviously we have to consider the moment that is causing maximum deformation at the middle. The point I is marked on the screen. Now, just to sum it up, point A, B, C, D, which are the support points, there we have zero deflection. Then we have at the midspan E, F, G, H, where we have maximum deflection. Out of that, the maximum will be at point I. And then we'll see how to design this against this maximum deformation and the hogging and sagging, right? Now, let us move over to the design, because now we have identified we have hogging moment here, sagging moment there, and again hogging moment here. And this is one direction. We have to consider the column strip as well as middle strip, right? So with that, let us see how we can design the structure. But before that, let us again also consider the shear in flat slab. This is again critical, because when we have a slab directly over a column, there is a sharp change in geometry. Obviously, there is a possibility of shear failure, as you can see here. So the initial crack starts not exactly at the face of the column, but somewhere very close to the column face, and then it goes like this. Then cracks start appearing, and then finally there is a possibility of punching, right? Now when we design the flat slab against shear force, recall we provided a drop. Why? Just to increase the depth at that location. So if you have a column head along with a drop, you basically provide this additional section which will offer the resistance against shear. So now let us see how the shear strength of this flat slab is achieved. So the shear strength of the slab is provided by the compressive resistance of concrete and the dowel action of the flexural reinforcement, right? So the critical section we'll see in a minute, and then what are the design requirements. Now, as per the design of the flat slab, as per IS 456, there are first certain requirements. The thickness of the slab, which is given in the clause 31.2.1. So the thickness of the flat slab shall be generally controlled by consideration of span to effective depth ratio given in clause 23.2.1. For slab with drop conforming to clause number 23.2.1b, the span to effective depth ratio shall be applied directly, otherwise this ratio shall be multiplied by 0.9. For this purpose, the longer span shall be considered. So when we consider the span to depth ratio, obviously we will consider the longer span. Recall L1 and L2, which one is longer we have to consider. But before that, we have to first find out the effective span length. That we will discuss in a minute. Now the minimum thickness of the flat slab must be 125 millimeter. Then the question of drop, if we provide drop, that is given in clause number 31.2.2, the drop when provided shall be rectangular or square in plan and have a length in each direction not less than 1/3 of the panel length. Okay, recall this, not less than 1/3 of the panel length in that direction. For exterior panel, the width of drop at right angles to the non-continuous edge measured from the center line of the column shall be equal to 1/2 of the width of the drop for interior panels. Obviously, for the edge columns, it will have only one side. So that's why it is 1/2 of the width of the drop for the interior panels. Then comes column head, which is given in clause number 31.2.3, where column heads are provided that portion of a column head which lies within the largest right vertex angle of 90 degree and can be included entirely within the outlines of the column, and the column head shall be considered for design purpose. Okay. Now, next comes the bending moment. Now, the bending moment in flat slab is given in IS 456 in the clause 31.3. For that, first the method of analysis and design. So it shall be permissible to design a flat slab by one of the following method, either direct design method or equivalent frame method. Now for the direct design method, the clause number is 31.4. It has certain limitations. There will be a minimum of 3 continuous spans in each directions. The panel shall be rectangular and the ratio of longer span to the shorter span within a panel shall not be greater than 2. Permissible to offset columns to a maximum of 10% of the span in the direction of the offset, notwithstanding the provision B, which is here. Then the successive span lengths in each direction shall not differ by more than 1/3 of the longer span. The end span may be shorter but not longer than the interior spans. And the design live load shall not exceed 3 times the design dead load. So these are the limitations for the first option. Now comes the total design moment for a span, which is given in 31.4.2. In the direct design method, the total design moment for a span shall be determined for a strip bounded laterally by the center line of the panel on each side of the center line of supports. The absolute sum of the positive and average negative bending moment in each direction shall be taken as M0, which is the bending moment, is W times ln divided by 8. So M0 is the total moment. W is the total design load. Recall, in this case, we have to consider complete dead load and then live load accordingly, and then apply appropriate factor over an area of L2 times ln. So ln is the clear span exceeding from face to face of columns, capitals, brackets or walls, but not less than 0.65 L1, where L1 is the length of the span in the direction of M0 or M0, and L2 obviously is perpendicular to L1. Now this is important. Sometimes we have circular columns. So for circular supports, it shall be treated as square support having the same area, which is given in clause number 31.4.2.3. So when the transverse span of panels on either side of the center line of support varies, L2 shall be taken as the average of the transverse spans. Okay. And when the span adjacent and parallel to an edge is being considered, the distance from the edge of the center line of the panel shall be substituted for L2. So These all give us the dimensions L1 and L2, and once we find it out, we can actually work out the total moment against which we have to design. Now, the moment we calculate total moment, next comes the question of negative and positive bending moment for hogging and sagging, which is given in clause number 31.4.3. So, the negative design moment shall be located at the face of rectangular supports, circular supports being treated as square support having the same area. Now, for interior span, clause number 31.4.3.2, an interior span, there the total design moment M0 in a direction shall be distributed in the following proportions. So, for negative moment, we have to provide 0.65 M0, and for positive design moment, we have to provide 0.35 M0. So, first we calculate M0 based on what? Based on the panel dimensions and the load it is going to carry. Then we distribute that total moment into negative and positive moment. Now, for end span, in the end span, the total design moment shall be distributed in the following proportions. So, M1, that is the interior negative design moment. So, recall, if this is the end span and here are the supports, these are the columns. So, we will have a negative moment here, a negative moment there, and then we will have some middle portion where we have the moment which is sine. So, M1 interior negative design moment is 0.75 minus 0.1 divided by 1 plus 1 by alpha c. So, this is the proportion of the moment for end spans. M2, that is the positive design moment, which is 0.63 minus 0.28 by 1 plus 1 by alpha c. Now, M3, which is exterior negative moment, which is here, and that is 0.65 by 1 plus 1 by alpha c. What is alpha c? It is the ratio of flexural stiffness of columns meeting at the joint to flexural stiffness of slab. So, this is the expression. So, we can easily find out alpha c, which is a non-dimensional number. The moment we find it out, we can find the proportions, which is here for M1, then for M2, and then finally for M3. So, once we evaluate these proportions, we can distribute this moment M0 accordingly to these three locations. Now, distribution of bending moment across the panel width. So, the bending moment at the critical cross section shall be distributed to the column strip and middle strip. Recall, we had column strips and the middle strips. So, for column strip, the clause is 31.5.5.1 to clause 31.5.5.3. So, the negative moment at the interior support is given here. The column strip shall be designed to resist 75% of the total negative moment in the panel at the support. And the negative moment at the exterior support is the column strip shall be designed to resist the total negative moment in the panel at the exterior support. So, in one case we have 75% and other case we have the complete 100%. Now, when the exterior support consists of a column or a wall extending for a distance equal to or greater than 3/4 of the value of 1/2, the length of the span transverse to the direction of the moment shall be considered to be uniformly distributed across the length L2. So, that we'll see in a minute. Then comes the negative moment at the exterior support. So, for the exterior support, the column strip shall be designed to resist the total negative moment, and then the positive moment, once we are done with negative moment, for each column strip shall be designed to resist 60% of the total positive moment in the panel. Okay. Then comes the middle strip, which is given in 31.5.4. So for the middle strip, that portion of the design moment not resisted by the column strip shall be assigned to the adjacent middle strip. Each middle strip shall be proportional to resist the sum of the moment assigned to its two half middle strips. And then finally, the middle strip adjacent and parallel to an edge supported by a wall shall be proportional to resist twice the moment assigned to half the middle strip corresponding to the first row of interior column. Right? Okay. So now comes equivalent frame method, which is given in clause number 31.5. Recall, previous one was the direct method and then equivalent frame method, and there we have different options for analysis. These are familiar to you. You have already done these analysis in your analysis course. So you can go for moment distribution, then Canny's method or stiffness method or similar techniques, right? Out of that, these days we have finite element analysis. So we always develop a FE model of the structure, and then using that we can go for a direct method of analysis and then find out what are the appropriate moments acting at different locations of the different strips. Now, there are certain assumptions in the equivalent frame method. So, in that, what are the assumptions? The structure is made up of equivalent frame on column lines. Each frame has a row of equivalent columns or supports and beams equivalent to slab width bounded by the center line of the panel on each side of the center line of the column or supports. Frames adjacent and parallel to an edge shall be bounded by the edge and the center line of the adjacent panel. So, effectively what we do, we assume that the strips are bounded by their edge lines, and we have to consider those strips as beams which are supported at the locations of the columns, or if you have wall, that is the support. And together they behave like a frame. So each such frame may be analyzed in its entirety, or for vertical loads, each floor thereof, and the roof may be analyzed separately, with its column being assumed fixed and at their remote ends. So this is the column. So if this is the slab at this point, and obviously at the bottom, we consider complete fixity, and thereby we analyze it. Recall the expression for M0, and then that we distribute at different locations with the appropriate proportions that we have already prescribed. Now, it may be assumed in determining the bending moment at a given support that slab is fixed at any support where two panels are distant from there, provided the slab continues beyond that point. Okay, so this is the continuity we have seen for a beam which is continuous over the support. A similar assumptions is here for this equivalent frame method. For the purpose of determining the relative stiffness of members, the moment of inertia of any slab or column may be assumed to be that of the gross cross section of the effective concrete alone. Recall, we have to calculate that alpha, that proportional stiffness, whatever we have in the slab and column, and we have to take the ratio to find out this non-dimensional number. There we have to consider the gross cross section of the concrete alone. Then variation of moment of inertia along the axis of the slab on account of provision of drops shall be taken into account. In the case of recess or coffered slab, which is made solid in the region of the columns, the stiffening effect may be ignored provided the solid part of the slab does not extend more than 0.15 L effective into the span measured from the center line of the column. The stiffening effect of flared column head may be ignored. So that is the provision, because these additional stiffness are actually as reserve strength. So we do not utilize them when we calculate the stiffness in the slab and column. Then comes the loading pattern, which is given in 31.5.2. When the loading pattern is known, the structure shall be analyzed for the load concerned. So when the load is, when the live load is variable but does not exceed 3/4 of the dead load, or the nature of the live load is such that all panels will be loaded simultaneously, the maximum moment may be assumed to occur at all sections when the full design live load is on the entire slab. So this is important. Not necessarily all the panels will be loaded with live load, but for the design purpose, we can use this and we can simultaneously load all the live panels, and then accordingly we can find out the maximum moment. Now for the consideration of live load, dead load ratio, and when panels are not loaded simultaneously, we have these options. So maximum positive moment near the midspan of a panel may be assumed to occur when 3/4 of the full design live load is on the panel and on alternate panels. Then maximum negative moment in the slab at the support may be assumed to occur when the 3/4 of the full design live load is on the adjacent panels only. Then minimum design moment option. In no case shall design moment be taken to be less than those occurring with full design live load on the panel. This is important. So after all these combinations, we have to find out the moments, and then again, obviously the question is negative design moments, which is given in clause 31.5.3. At interior supports, the critical section for negative moment in both the column strip and middle strip shall be taken at the face of rectangular support, but in no case at a distance greater than 0.175 L1 from the center line of the column. At supports, at exterior supports provided with brackets or capitals, the critical section for a negative moment in the direction perpendicular to the edge shall be taken at a distance from the face of the supporting element not greater than 1/2 of the projection of the bracket or capital beyond the face of the supporting. So this tells us the location. For circular or regular polygon shaped supports, we can have different types of columns that shall be treated as square support having same area. So when we have these type of support conditions, we have to convert that into square supports with same area, and then accordingly we have to satisfy this condition. Then the option is there in clause number 31.5.4 for the modification of the maximum moment. So moment determined by means of equivalent frame method for slab which fulfill the limitations of the direct design method may be reduced in such proportions that the numerical sum of the positive and average negative moment, recall at the support we have negative moment from two sides. So average negative moment is not less than the value of the total design moment, which is here. Right? So this was our starting point. Once we calculate this, then only we distribute. But we have to keep in mind about this clause that in no case the total positive and average negative moment shall be less than this value. Then comes the shear. The critical section for shear shall be at a distance d/2. D is the effective depth from the periphery of the column perpendicular to the plane of the slab, where d is the effective depth, when the opening in flat slabs are located at a distance less than 10 times the thickness of the slab from a concentrated reactions, or when the opening are located within the column strip, the critical sections specified above shall be modified so that the part of the periphery of the critical section which is enclosed by radial projections of the opening to the centroid of the reaction area shall be considered ineffective, and the opening shall not encroach upon column heads. So this is sometimes in the flat slab we provide opening. For the time being, I will not suggest you to go for this opening. So effectively what we have to keep in mind that at a distance, critical section is at a distance d by 2 from the face of the column, right, where d, small d is the effective depth. Now, how to calculate the shear stress? That is given in clause 31.6.2. Here are different shapes of the columns, as you can see, and the critical section, which are also marked by these dotted lines. So shear stress tau V, that is the nominal shear stress in the flat slab, is V, that is the shear force acting at that critical section, divided by B naught times D. B naught is the perimeter of the critical section. As you can see here, for every geometry it is marked. So if you have these type of geometries, first you find out B naught, then we already know effective depth. So B naught times effective depth is the effective area against shear force. So we can find out tau V. So when unbalanced gravity load, wind, earthquake or other forces cause transferring of bending moment between slab and column, a fraction 1 minus alpha of the moment shall be considered transferred by eccentricity of shear about the centroid of the critical section. So shear stress shall be taken as varying linearly about the centroid of the critical section, and the value of alpha shall be obtained from the following expression. So alpha is alpha 1 by 1 plus 2/3 square root of alpha 1, or A1 by A2. A1 is the overall dimension of the critical section for shear in the direction in which moment acts, and A2 is the overall dimension of the critical section for shear transverse to the direction in which moment acts. So accordingly we have to find out. Then comes permissible shear stress. Recall, earlier also we did the same thing. We evaluated tau V and then permissible shear stress, and then we checked whether our design satisfies or not. So when shear reinforcement is not provided, the calculated shear stress at a critical section should not exceed Ks times tau C. So what is Ks? Ks is 0.5 plus beta C should be less than equal to 1, where beta C is the short side by long side of the column. Then tau C is 0.25 square root of FCK in the limit state method of design, and tau C is equal to 0.16 square root of FCK in the working stress method of design. So we have to find out the tau C for that critical section, and then if the tau V is less than this, then we don't need to provide any shear reinforcement, and we'll design actually accordingly that, so that we don't need to provide any additional reinforcement, right? So when the shear stress at the critical section exceeds the value given above but is less than 0.15 tau C, the shear reinforcement shall be provided. If the shear stress exceeds 1.5 times tau C, the flat slab shall be redesigned, right? Shear stress shall be investigated at successive sections more distant from the support, and shear reinforcement shall be provided up to a section where a shear stress does not exceed 0.5 tau C. While designing the shear reinforcement, the shear stress carried by the concrete shall be assumed to be 0.5 tau C, and the reinforcement shall carry the remaining shear. Right? Okay, so then comes the slab reinforcement, which is given in clause 31.7. The spacing, this is important. Spacing of bars in a flat slab shall not exceed 2 times the slab thickness, except where the slab is of cellular or, for the time being, let us not, again, these are special options, let us not consider. So we have to keep in mind the spacing should not exceed, so S should not exceed 2 times the slab thickness. Okay. Now, area of reinforcement, when drop panels are used, the thickness of the drop panel for the determination of the area of reinforcement shall be lesser than the following. So, the thickness of a drop, or the second option is thickness of a slab plus 1/4 the distance between the edge of the drop and the edge of the capital. So, based on that, we have to first find out the area of reinforcement, and then we have to apply the spacing. We have to make sure that the spacing is maintained accordingly so that it is not greater than 2 times the depth. Now, obviously, when we design any reinforcement, anchoring of reinforcement is important. So, all slab reinforcement particular to a discontinuous edge shall have an anchorage. For that, we have straight bent or otherwise anchored past the internal face of the spandrel beam, wall, column. So, this anchorage is important at the edge section. For positive reinforcement, load less than 150 millimeter, except that with fabric reinforcement having a fully welded transverse wear directly over the support, it shall be permissible to reduce this length to 1/2 of the width of the support, or 50 millimeter, whichever is greater. Then for negative reinforcement, such that the design stress is developed at the internal face in accordance with, we have already discussed that earlier in section 3, where the slab is not supported by spandrel beam or wall, or where the slab cantilevers beyond the support, the anchorage shall be obtained within the slab. Right. Now, this figure is important. This figure is from IS 456, figure number 16. This talks about the different reinforcement strategies that we have to follow when we detail a flat slab. So, I will suggest you go through this guidelines, because accordingly we have to follow the detailing, right? Now comes an example. With that example, we'll see how we can actually design a flat slab. So for this, our design is focused on the interior panel. So this is the interior panel. Panel size is 6.5 meter by 6.5 meter. So this is a square panel. Live load is given 5.5 kilonewton per meter square. It is supported on columns which are circular. So the diameter is 350 millimeter. Concrete we use M20 and steel we use Fe 415. Now with this interior panel we provide drop. Then let us start the solution, see how to design this flat slab according to the guidelines that we have already discussed. So first is the thickness of the slab. Recall L by D. So D we provide L by 26. So length, it is a square panel. So 6.5 meter. So 6.5 into 1000 divided by 26. So D we get 250 millimeter. Now recall minimum thickness as per IS 456 is 125. So we can add up this thickness of 250 millimeter. Then comes the load calculations. First we have to calculate the self weight of the slab. For that we consider 25 kilonewton per meter cube of density, and then we calculate per meter square, it is 6.25 kilonewton. Then live load is already specified. So we can calculate W, which is the summation of these two, and then we have to find out the factor load, which is 1.5 times this summation of dead load and live load. So ultimately we get the factored load as 17.625 kilonewton per meter square. Then we have to design the drop panel. Minimum size, recall 1/3 of the span. So 1/3 times 6.5. So it is 2.2. That is the size of the drop panel. So we have a drop size of 2.2 into 2.2. Right. So the drop is designed. Then the bending moment calculation. For that, recall we need L1, L2, which is 6.5. Right. Then we have to find out Ln, which is 6.5, the panel size, minus the size of the column on either side. So it is 6.15 meter. Then once we find out the lengths L1, L2 and Ln, we can calculate the total load, which is W times L2 times Ln. And then total W, what we get here is 704.56 kilonewton. Recall this is factored simply because here this small w is factored. So the total design moment as per this direct formula, it is W times Ln by 8. So we can calculate that it is 541.63 kilonewton meter. So that is the total moment. Recall we have to distribute it. So for negative moment M1, it is 0.65 times M0, so which is 352.06 kilonewton meter. Then for positive, the remaining, so it is 0.35 times M0, which is 189.56 kilonewton. Then once we find out negative and positive moment, we have to go for moment distribution in column strip and middle strip. So the total design moment are further distributed into column strip and middle strip. So width of the column strip, which is 0.25 times L2, which is 6.5. So that is 1.625 meter. So twice of this, because this is on one side. So 6.5 is from here to there. So this is 6.5. And then 0.25 times that. So this is the size. So on either side we have to consider. So the column strip will have a dimension 2 times 1.625, which is 3.25 meter. Then the bending moment in the column strip. So the negative bending moment is 0.75 times in M1. Recall M1 we have already evaluated here. So 0.75 times M1, which is 264.045 kilonewton meter. And then positive moment is 0.6 times M2, which is 113.742 kilonewton meter. Similarly, for the middle strip, we have negative moment, which is 0.25 times the value we have calculated here. And that is 88.015 kilonewton meter. And for the positive moment, it is 40%. So which is 75.828 kilonewton meter. So now we know the moments acting in column strip and middle strip, and we also know the negative and positive moment. So we can design the section, right? So let us first check the thickness. So for the drop panel, we have to consider the negative moment, which is 264.045 kilonewton meter. And then for the flat slab portion, the positive moment, which is 113.742 kilonewton meter. Then we can calculate the thickness. For the drop panel, we are familiar with this expression, design against bending. So we can find out the effective depth, so which is here. So effective depth we get 208.53 millimeter. So we have to provide some additional depth for safety and of course for punching shear. So adapt the drop of 330 millimeter. So effective depth from here you can calculate, which is 309 millimeter, right? Okay. Now comes thickness of the slab using positive moment. So for that we know the value of the positive moment, and then we can calculate again the effective depth, which is 136.9. So provide a slab depth of 160 and the effective depth in that case will be 139. Okay. Then we can find out the area of the steel. For the column strip, we can find out the area of the steel. This expression again all of you know. So you use M20 and Fe415. Then we get the AST of 2800 millimeter square, and then we provide the spacing. Recall the way how to calculate. We can find out the area of each bar, we can find out the number of bars, and we can find out the spacing. So we provide 20 millimeter phi at the rate of 110 center to center, right? Recall this is for the column strip which has a width of 3.25 meter, right? Okay. So similarly for the negative bending moment, again we can find out the AST, which is 2036 millimeter square. So for that we provide 16 phi 220 center to center plus 18 phi. So it's a combination of two different steels that we provide. We can provide higher diameter bar, but recall there is a guidelines for maximum spacing. S should not be greater than twice D, right? So you have to keep that in mind. Here in this case, AST provided from 16 phi bar and 18 phi bar, which is 2070 millimeter square. So that is okay. Similarly, for the negative bending moment, we know the bending moment we have already evaluated. We can find out the area of the steel and we can find out the spacing. In this case, we provide 25 bars and 18 phi bars. So the total area provided here is 2584 millimeter square, which is more than the required. Then we come to the middle strip. Again, for the middle strip, we know the bending moment, and then we can find out the area of steel, which is 1710 millimeter square. So what we do, we provide 16 phi bar at the rate 100 center to center, right? Okay. Then the final check, we have to check for shear, because we have already designed the reinforcement for bending. Now for the shear, first we have to find out the critical sections. Recall the codal provision I showed you earlier. Here we have the critical section marked for circular columns. So accordingly we find out the total area, that is here it is, recall, B0 times D, right? So that we find out first. So diameter of the critical circle we can find out, which is 659 millimeter. Then the load on the column, first we find out. So load on the column is 702.69 because we have already evaluated the UDL per area. So we can find out the total load acting. Then tau V is the total load divided by this area. And the moment we find out tau V, which is 702.69 divided by pi D times, this is the diameter of the critical section, times D effective, right? So that is what we do here. So the effective depth is 309. So we find out the tau V, which is 1.098 Newton per millimeter square. Now next is permissible stress, which is tau C, that is 0.25 times square root of FCK, which is 1.12 Newton per millimeter square. So that means it is okay, because our tau V is less than tau C. Now we have to repeat the same for the critical section in slab. That you can see we have identified that critical section. Okay. So we have the support lines from there. This is the critical section. So the total perimeter of the critical section we can find out. In this case it is 9.356, which we get from the geometry. You have all these details. Then total shear in that region also we can find out, which is 648.23 kilonewton. Then we can find out tau v. In this case, it is 0.498 or 0.5 Newton per millimeter square. So this is again less than tau c, which is okay. So we have designed against bending for all components, whether it is column strip or middle strip, and for positive and negative bending moments. Then we have checked the critical section for shear near the column face and in the slab. Here comes the detailing. You can see we have for the center panel, again not for the other panels. For the center panel, we have all bars marked. See, this time we have a slightly different way of marking the bars. So we have identified all the bars and their diameter and spacings are marked here. So we have bars for the column strip, bars for the middle strip, and all bars are marked accordingly. We have to provide in the construction, right? Now let us see the cross section. So for the middle strip, here is the cross section. Here again, all bars are marked. See some bars which are actually bent upward, because at the support we need more bars on the upper face, because we have hogging moment here, while at the middle we have no bars here, but all the bars are here because we have sagging moment there. So some of the bars from the middle part is actually bent up to meet the requirements at the support. And you see these bars are carteled here. I showed you the option given in figure 16 of IS 456. So you have this detailing as per that drawing. We have detailed it out. So we have this circular column with a drop panel, which is of size 2.2 meter. Recall that is the first thing we designed at the beginning. And then on top of drop panel, we have this bars. So now for the column strip also, we have this option. So for the column strip, we have all bars identified, all bars marked according to the design values that we have already identified. Right. So that completes the design of flat slab, and all the steps are outlined here. So what I suggest, you go through all these options. It is not difficult. The only thing is you have to step by step find out all those component moments, and then accordingly you have to find out the critical sections and then find out the design against shear. Of course, if the cross section is not sufficient enough to provide adequate tau c, then you have to go for the shear reinforcement. But in this example, we have tau v is less than tau c. So that is, we always try to actually design so that the cross section, the concrete itself is sufficient enough to provide adequate strength against shear. So if you have any doubt, do let us know. We will clarify your doubt. You can design flat slab with other panels and with other geometry of say column. Okay. Only thing you have to remember, you have to consider all the options for bending moment and shear force, what is outlined here. And we have designed this interior panel using direct method. You can go for a detailed analysis using finite element, which normally is covered in the 4th year of your undergraduate curriculum, and that's why it is not covered here. So for the time being, you can go for direct options as prescribed in IS 456. Thank you very much.